Now, in our previous session we discussed about different vector operations like vector addition and vector subtraction. Now, we are going to discuss about vector multiplication and different operations on vectors like differential operator and integral operator on vectors. Now, we will start this session with vector multiplication. The vector multiplication is a little bit a different thing as compared with the scalar multiplication. If we are considering two scalars, let us take k1 and k2 are two scalars, then a simple multiplication is possible between this k1 and k2 as just k1 k2. But here if you are considering two vectors a bar and b bar, the multiplication is not that much easier than as easy as our scalar multiplication. So, what we have to do is we have to learn how to multiply two vectors and what are different forms of vector multiplication. Here basically two different vector multiplications were defined, that is dot product. The product between two vectors is dot product or scalar product, and a cross product or vector product. So, these two are the two different multiplication techniques in our vector multiplications. Now, one by one we will discuss about this dot product and cross product in all different forms. So, let us take a bar and b bar are two vectors, then how the dot product was defined between these two vectors. So, let us take the a bar is like this and b bar is like this. So, these two are two vectors and they are in different directions and they have different magnitude. Let us consider the angle between these two as theta AB. Then simply the dot product between these two is defined as a bar dot b bar. The notation for the dot product is a simple dot. A bar dot b bar is equals to magnitude of a bar multiplied with magnitude of b bar and cos of angle between those two, that is cos theta AB. Just if you observe the result what we got for this dot product, the magnitude of a bar is a scalar, magnitude of b bar is another scalar, and cos of this theta is nothing but a scalar. So, scalar multiplied with all scalars will gives you a scalar. That is why the dot product is also called as a scalar product. Now, this is a simple graphical representation of the dot product. Whenever we are considering a bar and b bar as two vectors which are given drawn like a line, then this is a very easiest procedure to obtain the dot product. Now, if the two vectors are given as a point, how to obtain the dot product? Before that, what we do is just we will examine this dot product for different unit vectors in all coordinate systems. So, let us consider the rectangular coordinate system. In the rectangular coordinate system, the unit vectors in x, y, z directions are ax, ay, az. So, if we consider the dot product between all combinations, the different vectors of our rectangular coordinate system, then what we get? Let us take ax dot ax. So, as per the definition of our dot product, clearly you can write this one as ax, magnitude of ax, once again magnitude of ax, and cos of angle between ax and ax. So, obviously the angle between ax axis and the same ax axis is 0. So, which is equals to 1 into 1 into 1, just 1. So, if we are multiplying two unit vectors which are in same direction, then the answer is 1. In the same way, if you examine the next vector ay dot ay, so which is equals to that ay magnitude, so the magnitude of ay multiplied with the cos of angle between ay and ay is 0, which is also equals to 1. So, if you take this general observation, what you can say is the multiplication of two unit vectors with the dot product always gives us 1. Then what is the other combination we can take? If we are considering the other combination like ax dot ay, which is equals to, as per our definition, magnitude of ax, magnitude of ay, cos of the angle between ax and ay. Here what we are doing is always we are using our right handed coordinate system and it is orthogonal coordinate system. Since it is orthogonal coordinate system, the angle between x and y is always 90 degrees. So, it is cos 90, which is 1 into cos 90 is 0, simply the answer is 0. So, what we can say is, I am not taking the remaining all combinations. If we take the remaining all combinations, obviously what you will get is 0 here. So the general statement for product of our unit vectors will be like this with the dot. So if you are taking a similar unit vector, then what we will get is 1. If you are taking two different unit vectors which are orthogonal, then the answer is 0. So clearly what you can say is, for orthogonal unit vectors or any orthogonal vector, the dot product always becomes 0. So this is for our rectangular coordinate system. The same principle is applicable for our spherical and cylindrical coordinate system also. So if you consider the unit vectors in our cylindrical coordinate system, that the unit vectors in our cylindrical coordinate system are a rho, a phi, a z. So here also, if you apply the dot product for all the vectors in different combinations, that is a rho dot a rho and a phi dot a phi, which is equals to az dot az, always these are equals to 1. And if you are considering the different combination like a rho dot a phi and a phi dot az and az dot a rho, which is equals to 0. That's simply what you can observe. Now if you are considering the spherical coordinate system, the unit vectors are ar, a theta, a phi. So these are the unit vectors in our spherical coordinate system. The same combination is applicable here also, that ar dot ar is equals to a theta dot a theta is equals to a phi dot a phi equals to 1. The same way ar dot a theta is equals to a theta dot a phi equals to a phi dot ar, which is equals to just it is 0, right? So clearly if you are taking any coordinate system and the respective unit vectors in that particular coordinate system, you can apply a dot product in an easiest way, right? Now if you are considering the point form of any vector, so this is all the graphical representation are just we are considering the vectors as lines. Now if you are considering the point form of two vectors, let us take a bar as a point that I am taking as ax, ay, az, and b bar is equals to bx, by, bz. How to get the dot product between two vectors when they are given in point form? Just you apply a point to point multiplication with the dot product, that is a bar dot b bar is equals to, write down this one as a vector in terms of its unit vectors like ax, ax. That's since it is represented in rectangular coordinate system, this will be written as ax, ax plus ay, ay plus az, az dot bx, ax plus by, ay plus bz, az. Right. Now what you have to do is just you have to multiply this one. It's a point to point, a term to term. Then if you are multiplying this ax, ax with this entire term, then what we will get? Ax, bx, that's the two constants or the two parameters ax, bx, and the dot product will be taking place between ax and ax, that is ax dot ax, plus this ax, ax, that is ax is multiplied with by, and the dot product will be taking place between this ax and ay, that is ax dot ay, plus the third term is ax, bz, this is ax dot az. I am not writing the remaining terms, just we will observe first what happens to this and then we can write the remaining terms. Ax, bx, ax dot ax, obviously ax dot ax is 1, and this ax dot ay, as already we learned that one as 0, this ax dot az is also 0. So if you observe the multiplication of this term with the remaining entire vector b, then what we get is the combination ax, ay and ax, az goes to 0. The term which has in the same direction remains for us, that is only ax, bx left for us, ax, bx. In the same way, if you consider the second term and with the multiplication of the b, what we will get is ay, by, and the third term will give us az, bz. So clearly observe here, this is a scalar quantity. Here we are not getting any vector, that a bar dot b bar always gives us a scalar as result. Now what happens if we are considering b bar dot a bar? Let us consider that b bar dot a bar also. Then this is bx, ax plus by, ay plus bz az, that the vector b was written first, and then next vector a, ax plus ay plus az az. Now just you observe generally bx multiplied with ax, that is only the term which remains for us if you are taking this term product, and the remaining all are by, that what you can write, by ay plus bz az. Just you observe this term what we got just now and this term what we got are same. So what you can say is this a bar dot b bar is equals to always b bar dot a bar. So whenever you have a dot product, no problem, you can interchange the vectors. So this is a introduction about a simple dot product and the application of this dot product for different coordinate systems. Now we will go for another multiplication method called as cross product. Now we will discuss about cross product between two vectors. Let us take a bar and b bar. These two are two vectors. Then how the cross product between these two is defined? That the notation for that cross product is cross between these two vectors, that is a bar cross b bar. Simply it is defined as magnitude of a bar multiplied with magnitude of b bar, sine of angle between them multiplied with a normal vector, a normal unit vector which is perpendicular to both a bar and b bar. So what we have to do is you have to represent always the product with a normal unit vector. How to obtain that normal unit vector? Just we will know. Now consider this a bar. Let us take this is a bar and another vector b bar with another magnitude and direction can be written like this. Then the product is, the cross product is a bar magnitude of a bar we will consider, magnitude of b bar we will consider, and sine of the minimum angle between them, that this is the minimum angle between them, that is theta ab will be applied. Now how to obtain that an normal unit vector? To observe that normal unit vector always we need to follow the right-handed thumb principle. So whenever we are taking the cross product, we must learn about the right-handed thumb principle and we must remember that the direction always follows the thumb when the folded fingers are placed from the first vector to the second vector. That we need to place the folded fingers from first vector to second vector, and then the direction of thumb always gives us the direction of this normal unit vector. Then how to obtain that one? For our understanding, I am writing this direction as a to b. Since the first vector is a and the second vector is b, I am writing this direction from a to b. Keep your folded fingers from a to b, that the folded fingers are drawn from or taken from a to b. Then what is the direction of our thumb? The direction of our thumb is going into the plane of both. So here the result is always going into the plane of both. So the cross product is having a result at some magnitude which is equals to this term, and the direction is playing also going into the plane of our board. If you will take another example, let us take this as a bar and this as b bar. Now once again I am calculating that a bar cross b bar. For this case, if you are calculating the a bar cross b bar, once again consider the magnitude of this one, a bar magnitude of b bar, and our sine of angle between them, that is sine of theta ab, an. That's the magnitude is same as our previous one if you take the same vectors. But what is the direction of our a bar cross b bar? Here in this case, place your folded fingers from a to b. Just what I am doing is I am placing the folded fingers from a to b, then observe the direction of thumb. If you observe the direction of thumb, it is always pointing outwards the plane of board. Since it is pointing outwards the board, just represent the result as outwards the plane of board. That it is coming outwards the plane of board and it is going into the plane of board. Now if these two vectors are same, that a bar and b bar are same in magnitude, then a b sin theta ab will gives you the same result in both cases, that the magnitude is same, but in this case it is going into the plane, in this case it is going out of the plane. So clearly what you can say is, if you are considering a bar cross b bar by interchanging the vector positions, then what you can understand is a bar cross b bar is equals to minus b bar cross a bar. Or for clear understanding, what we do is just we will consider b bar cross a bar in this case, then it is a little bit convenient to understand. So what I do is I will take the same vectors and I will try to obtain B bar cross A bar. So let us consider A bar again, and this is our B bar. In this case what we did is we calculated A bar cross B bar. Now calculate B bar cross A bar. That like this, theta AB is same, then B bar cross A bar is equals to the magnitude of B bar, magnitude of A bar, sine of angle between them, sine of theta AB, A n. That the unit normal vector is now clearly observe, it is coming out of the plane of board. Since it is coming out of the plane of board, we need to represent it like this. That what I did is I took the same vectors A bar and B bar and I have applied A bar cross B bar here and B bar cross A bar here. So if you observe the magnitude is same, the magnitude is equals to the same quantity, but the direction is opposite to the previous one. So clearly this principle, let's say A bar cross B bar is equals to minus B bar cross A bar is applicable whenever we are taking cross product between two vectors. So this is easy for graphical representation, that if you have angle and magnitude, graphically you can calculate the cross product between two vectors. That if you are considering point form of our vectors, so let us take A bar is equals to, I am considering them in rectangular coordinate system. Let us take A bar is equals to Ax, Ay, Az. B bar is equals to Bx, By, Bz. Then what I want is A bar cross B bar. So this A bar cross B bar, once again same as in our previous one, what we need to do is we need to go for a point to point cross product. So to go for that point to point cross product, we need to understand what is the cross product between two unit vectors. For that, before this, what I do is I will discuss what is the cross product between all the unit vectors in a rectangular coordinate system. So let us take the rectangular coordinate system has unit vectors Ax, Ay, Az. Once again, what I want to do is I want to take all the combinations for this cross product. Consider Ax cross Ax, which is equals to, as per our definition, magnitude of Ax, sine of angle between this Ax and Ax is always 0 with a normal vector An. So 1, 1, sine 0 is 0, An, which is equals to just 0. In the same way, if we consider Ay cross Ay, then Az cross Az also be 0. So if you take the two vectors which are in same direction, whatever it may be, that may be either unit vector or any other vector, if you are considering two vectors which are in same direction, then the cross product always will be 0. If you take any other combination, let us take the other combination Ax cross Ay. So Ax cross Ay is equals to magnitude of Ax, magnitude of Ay, the sine angle between x and y, the angle between x and y is 90 degrees multiplied with a unit vector which is perpendicular to both Ax and Ay, which follows right handed thumb rule. So now observe the magnitude first, which is equals to 1, 1 and sine 90 is 1 An. Now we need to observe this An. So this An can be observed with the simple, once again, right handed thumb rule. What I have to do is I have to place right hand from first vector to second vector. The first vector is here Ax and the second vector is Ay. So what I am doing is I am placing the thumb from first vector to second vector. If I am placing the thumb from first vector to second vector, folded fingers from first vector to second vector, the thumb always goes in the direction of z. So the normal unit vector what we are considering is Az. That what we can consider. So Ax cross Ay always gives another unit vector, the magnitude is unity here, another unit vector which is perpendicular to both x and y, and it is satisfying right handed thumb rule. So Ax cross Ay is equals to Az. The same way, if you consider the remaining all combinations, what we get is Ay cross Az is equals to Ax, Az cross Ax is equals to Ay. That if we are considering the all combinations in the respective order, that is from x to y, y to z, then what we get is the third vector which is perpendicular to both. If we consider in reverse order, that is if I consider Ay cross Ax, let us consider Ay cross Ax. If we are considering Ay cross Ax, once again apply the formula magnitude of Ay, magnitude of Ax, Sine of angle between y and x is obviously 90 degrees a n. That is the unit vector. Now we need to find out for this y and x, which is perpendicular to both y and x. Now the magnitude is 1 1 1 a n. Now once again place your folded fingers from y to x, that is from first vector to the second vector. If you are placing the folded fingers from y to x, then now the folded fingers are along this direction, from they are moving from y to x. Then what is the direction of our thumb? Clearly it is in negative z direction. So this now this a n can be written as minus az. So if you observe this one, ay cross ax is equals to minus az, that is the opposite to the original direction, that what we discussed earlier for our a and b. Ax cross ay is equals to az and ay cross ax is equals to minus az. Now this combination is applicable for remaining all coordinate systems also. What we need to do is we need to consider in their respective order x to y z, y to z x, z to x y. To simply remember that one, I will give you a circle. That will be useful for remembering all the combinations. Later we will go for this a bar cross b bar in point form. Just I will give you a circle. With that circle we can easily remember what is the combination of cross product for all the coordinate systems. Let us take this is az, ax and ay. That is a right handed coordinate system, that what we are considering. Now form a circle like this, that is from x to y, y to z, z to x in their respective order. If you consider the cross product between them, ax cross ay always gives the opposite one, that is az. Ay cross az always gives its opposite one, ax. Az cross ax always gives its opposite one, ay. If we are moving in opposite direction, just you consider the opposite direction vector to it, nothing more than that. If you are moving like this, that is ay cross ax, then what we get is minus az. So if you are moving like this, that is from z to y, what we get is minus ax. If you are moving like this, that is from x to z, what we get is minus ay. So there is a very simple circle. If you remember this simple circle representation, then easily can observe what is the cross product between all the unit vectors for all coordinate systems. In the same way, I will write the circle for remaining two coordinate systems, that is cylindrical coordinate system and spherical coordinate system. So let us take the unit vectors are a rho, a phi, az in our cylindrical coordinate system. If you apply the cross product between all these unit vectors in the respective order, a rho, a phi, az, that what I am considering. A rho cross a phi is equals to az, a phi cross az is equals to, this is a rho, and az cross a rho is equals to a phi. So if you are considering the opposite direction, obviously the vector goes to the negative. In the same way, if you are considering our spherical coordinate system, a r, a theta, this is a phi. So a r cross a theta is equals to a phi, a theta cross a phi is equals to a r, a phi cross a r is equals to a theta. So clearly observe here, so whenever we are considering the cross product between the unit vectors, only a cross combination is possible. There will be no combination for the similar vector ax cross ax, ay cross ay, az cross az is not at all possible. Now with this one we will go for the vector multiplication for a point form. Let us consider the two vectors a bar as ax plus ay plus az and another vector b bar as bx plus by plus bz az. Now what I have to do is I have to get the cross product between these two. For that, consider a bar cross b bar. Here what I am doing is same as our previous one, I will consider a point to point multiplication with their unit vectors. So the first term, that is ax bx is the magnitude, the cross product is ax cross ax, plus ax by is the magnitude and the cross product is between ax cross ay, plus the third one ax with bz, that is ax bz, the cross product between ax and az, that is ax cross Az, plus if you go to the second term, it's a ay with all these terms, az with all these terms. That's a we can examine later, no problem. But examine now what is this first term. If you observe this ax cross ax, obviously what you will get is 0. That ax, this ax cross ay is az. Ax cross az is minus ay. Like that, in the remaining two terms, what we get is 2 plus 2 plus 2. So the total 6 terms will be appeared for us. If you write those 6 terms, then we will get a matrix, or that's nothing but the determinant of this matrix. How to write down the determinant? Simply the determinant can be written like this. First you write down the unit vectors in all directions. That is ax, ay, az in the respective order. Next write down the components of first vector. The components of first vector are ax, ay, az. And the components of second vector will be written here. That is bx, by, bz. If you calculate the determinant of this one, that is the result of your a bar cross b bar. So obviously if you observe the result, what you can observe? Ax multiplied with ay bz minus az by minus ay multiplied with ax bz minus bx az multiplied with ax by minus bx ay. So here clearly every term what we are considering is multiplying with one of the unit vectors, any one of the unit vectors. So clearly the answer is a vector. That's why this cross product is called as a vector product. So whenever we are considering cross product between two vectors, obviously the result is a vector, right? So clearly with this introduction, it's the vector multiplication like a dot product and cross product can be done between any vectors. So if you are considering two vectors, these are the different combinations what we have. Now we will move to the vector multiplication for three vectors. So if you are considering three vectors, how we can apply or how we can multiply those three vectors in different forms. That is vector triple product. First we examine what is the triple product and what are different combinations which exist for us, and then we will go for the result of particular thing. Here what I am doing is I am writing all the combinations for a product of or three vectors. Let us consider a bar, b bar, c bar. These three are three vectors what we have. Now what I do is I will take different combinations between these three vectors. That is the multiplication combinations are dot cross, cross cross, dot cross dot, dot dot, like that. So first one, what I do is I will take the dot combination. So a bar, b bar dot c bar. The second one is dot cross combination. The dot product, dot product, dot product, cross product. Third one, cross dot, a bar cross, b bar dot c bar, that what I can consider. Last one is cross cross, a bar cross, b bar cross, c bar. Here all the a bar and b bar, c bar are vectors. Now observe, first we need to examine whether they exist or not. So if it is a valid one, then only we have to go for the result, right? Observe this one, a bar dot b bar dot c bar. What is b bar dot c bar? Always the dot product gives you a scalar. So dot product between a scalar and vector, it is not at all defined. So clearly this product is not defined. So we are not supposed to consider this type of product between three vectors. The second one, b bar cross c bar. Always b bar cross c bar will give us a vector, right? So the vector multiplied with another vector with dot product. So vector dot vector, it is defined. This is a dot product. So this combination is possible. And a bar cross b bar dot c bar. Once again this b bar dot c bar is a scalar. So the cross product between vector and scalar, it is not possible. So since it is not possible, this is not a valid combination. And the final one, a bar cross b bar cross c bar. So this b bar cross c bar is a vector, vector cross another vector. This is also a suitable or a correct combination, that what we need to consider. So if the examiner asks to identify which among the following is not valid, you need to identify that this is not valid since the dot product between scalar and vector is not possible, and this is also not valid since the cross product between scalar and vector is not possible. So these two are the options which are not valid. Now among all these, that is the existing two, this one and this one, which one gives which result? The scalar answer is for what and the vector answer is for what? That we examine once again. That B bar cross C bar is a vector. Vector dot vector, always the dot product gives us a scalar. So for this the answer is a scalar. Now observe here, B bar cross C bar. That B bar cross C bar is a vector. Vector cross vector. Vector cross vector always gives a vector answer. That the cross product is a vector. So here clearly if you observe, this particular triple product is called as scalar triple product, and this triple product is called as vector triple product. So if you consider the remaining all combinations, just they are not at all valid. Now we will observe what is the answer for this one and this one. That's the scalar triple product. That A bar dot B bar cross C bar. So as we know, A bar dot B bar is equals to B bar dot A bar. That you can swap the two vectors in our dot product. You can swap these positions of the operators also. No doubt about it. So here clearly this can be written as A bar cross B bar dot C bar, and the same way you can write this one as C bar dot A bar cross B bar. So just remember, for the scalar triple product we can swap the operators or we can swap the position of the vectors, and the answer can be written like this. Always a magnitude will be considered. Ax, Ay, Az, they are not unit vectors, they are the components of A, and Bx, By, Bz, Cx, Cy, Cz. So this is the answer of our scalar triple product. After calculation of this determinant, what you will get is a scalar, the vector triple product. Let us consider A bar cross B bar cross C bar. Here we are not supposed to change the location or the position of these two vectors as our wish. Since A bar cross B bar is not equals to B bar cross A bar, so leave it as it is. So A bar cross B bar. See, this can be remembered with this simple formula: B bar A bar dot C bar minus C bar A bar dot B bar. Here what we need to do is we need to take the dot product between A and C. That you will get a scalar. Multiply or vector with scalar. There is no operation here, just a simple multiplication. Next, A bar dot B bar will give us a scalar. Multiply this C bar with that particular quantity. Now subtract B bar scalar minus this C bar another quantity. Then what you will get is a vector. That's what is called as a vector multiplication, a vector triple product. Now this can be easily remembered with this simple formula: BAC back CAB. BAC CAB, back cab rule. So whenever there is a triple product of the vectors with all cross combinations, then immediately you have to recollect this back cab rule, that the vector A bar, B bar, C bar can be related with this one. So these two are vector triple product and scalar triple product. So with this one, the vector multiplication was over. Now we are going to observe different operations on vector and scalar. So since we have our mathematical electromagnetic equations are involved in many mathematical equations, we need to go for different operations on those equations to get a proper form. And so to get those proper form, we need to learn some basic operations on the vectors as well as on scalars. For that, what we do is we will introduce some differential operators and some integral operators which will be applied on our vectors. First we will discuss our vector operator, vector operations with differentiation. They are called as vector differential operator. That for this, what we do is we will use a basic differential operator called as del. So this will be called as either del or nabla. So this is a vector operator. So this vector operator can be applied on a scalar, or the same vector operator can be applied on a vector. So if it is applied on scalar, what it is called? If it is applied on a vector, what it is called? We will examine that one and we will interpret that one also. Before that, how it was defined? So this was defined in all coordinate systems. In the rectangular coordinate system it was defined, in spherical and cylindrical also it was defined. So in the rectangular coordinate system it was defined as dou by dou x in the direction of x plus dou by dou y in the direction of y plus dou by dou z in the direction of z. So clearly if you observe this one, this is a vector operator, this is not a scalar operator, this is a vector operator. And in the cylindrical coordinate system it was defined as dou by dou rho in the direction of rho plus 1 by rho dou by dou phi a phi plus dou by dou z a z. And in the spherical coordinate system it was given as dou by dou r a r plus 1 by r sin theta. It's a 1 by r sin theta is for phi. For theta it is just 1 by r. 1 by r dou by dou theta of a theta plus 1 by r sin theta 1 by r sin theta dou by dou phi of a phi. So this is the definition of our del operator in rectangular coordinate system, cylindrical coordinate system and spherical coordinate system. As per our requirement, what we have to do is you have to take this del operator and apply on the vector or scalar what we have. So what we need to do is just we need to observe in which coordinate system the point or the function is given to us, and based on that one we need to choose any of these three. Right, now we will observe what are different operators which can be done with our del operator. What are different operations? So the del operator can be applied on scalar. So if you are applying on a scalar, there will be no any other extra operations, only the del on a scalar. Let us take V is a scalar and A is a vector. Here A bar is a vector, that what I am considering, and V is a scalar. If you are applying this del on a scalar, that is del V, simply there will be no operation between them. Del of V, this is also called as gradient. In short, it can be written as grad. Gradient of V, where V is a scalar, clearly remember that point. So this is the first one what we need to observe, that it is applied on a scalar. If it is applied on a vector, as we said, there is no simple product between two vectors. If you are considering the operation between two vectors, that may be either dot product or cross product. So del dot A bar, this is one thing, and del cross A bar, this is the second operation what we have. So if the dot product is taken, what it is called? Divergence. Divergence of A bar. If the cross product is taken, curl of A bar. Just we need to observe what is the significance of this gradient, what is the significance of this divergence, what it gives, what is the significance of our curl, and how they are defined in all coordinate systems. If you learn the operation, then it is very easy to analyze our electromagnetic equations. That's why we need to learn the basic form first, right? We'll start with our gradient. That how the gradient can be written. I'll consider one coordinate system, and the same concept will be applicable to the remaining all coordinate systems. So what I do is initially I will consider the rectangular coordinate system, that is a little bit easy to understand, and the same concept we will extend to the cylindrical and spherical. So take this del operator in a rectangular coordinate system. How it is given? Dou by dou x ax plus dou by dou y ay plus dou by dou z az. Just here what we are considering is V as a scalar. I am not taking any vector component here, just V is defined as a function of x, y, z, and it is a scalar, it has no direction. Then what you can write? Just this V will be differentiated with respect to x, that V will be differentiated with respect to y, and that will be differentiated with respect to z. So this can be written as dou V of x, y, z by dou x in the direction of x plus dou V of x, y, z dou z dou y in the direction of y plus dou by dou z of V of x, y, z in the direction of z. So obviously after differentiation what we get is some constant here, or a function of x, y, z, that is, let us take c1 ax plus let us take another constant or a function of or x, y, z, what we get? c2 ay plus in the same way here it is c3 az. That c1, c2, c3 may be constants or function of x, y, z, right? Now if you observe the result of this gradient of V, what we are getting is a vector. So if you apply this del operator on any scalar, what we are getting is a vector. Now what this vector gives? This dou by dou x, dou by dou y, dou by dou z will gives us the rate of change of this particular scalar quantity. Now the entire result will gives us the maximum rate of change of a particular scalar. So in which direction that particular scalar is rapidly varying, in which direction we are getting the maximum rate of change for that particular scalar quantity. If we are taking an example of temperature, let us take on the surface of our earth, the temperature is there, the temperature is clearly a scalar quantity. Now if you want to know in which direction the temperature is rapidly varying, that we have to apply this gradient operation on that temperature function. So if you apply this gradient operator on the temperature function, then you will get a direction. Clearly we can understand that in the direction of the vector what we got, the temperature is rapidly varying. So this is the major application of our gradient function. It gives the maximum rate of change of a particular scalar quantity in a given direction or in a particular direction. So that is our gradient. In the same way, instead of this dou by dou x, dou by dou y, dou by dou z, you can take our dou by dou rho, dou by dou theta and dou by dou phi and dou by dou z for our cylindrical, and in spherical coordinate system also we can define same del operator as we written in our previous slide. Right. Now I will go for the second operator. The second operator is the divergence operation. The divergence operation is purely on the vectors, not on scalars. So what I do is I will consider a vector a bar, and as I said, if you are considering dot product between this del operator and ar, then it is called as divergence. So some of the people may get confused between this divergence and curl and the operations. If we are taking dot product, divergence, cross product, curl, they may think that it's in a confusion, dot product goes to curl and cross product goes to divergence. Don't get confused. Here I will give you a shortcut to you. Dot product always divergence, d for d. In the same way, del cross a bar, which is equals to curl, cross product curl, c for c. So d for d, dot product, divergence, cross product, curl. It's a very easy to remember, and after that one we will go for divergence. Let us consider a bar as a vector. Now we will discuss the divergence. Del bar dot a bar, which is equals to, in short form it can be written as divergence of a bar. Here what I do is, once again I will consider a simple coordinate system, rectangular coordinate system, and I will take this del operator in rectangular coordinate system, a in rectangular coordinate system, and I will apply the dot product between them. Then observe what happens here. If I consider the del operator in rectangular coordinate system, dou by dou x of ax plus dou by dou y ay plus dou by dou z az dot, the components of our a bar are ax plus ay plus az right. The dot product between the similar components will be taken place, remaining all components can be 0. So simply what you can write here as dou by dou x of ax, dou by dou x of ax plus dou by dou y of ay plus dou by dou z of az. So just observe here, what we are getting is a scalar quantity. Here there are no unit vectors. There are no unit vectors ax, ay and az. Just what we are getting is the rate of change of ax, rate of change of ay, rate of change of az. So clearly the answer is a scalar. Then what you can observe from this divergence, we are getting some quantity. The divergence always gives, clearly remember, the divergence always gives a quantity which is leaving the volume. That let us consider we have a volume, a differential volume is there, a small volume we have, some quantity is passing through this volume. Let us take a bar is the field which is passing through that particular volume. Now if you want to calculate how much volume is passing through the particular volume, or how much volume, how much quantity is, or how much field is leaving the particular volume, then what you have to do is you have to apply the divergence. So if you apply the divergence, definitely you can understand or you can observe how much quantity is leaving. Here we are not getting any direction, but how much quantity is leaving from a particular volume. If it is not leaving, if it is entering the volume, then also it is called as divergence, but it is called as negative divergence. And some quantity is entering the volume, the same amount is leaving the volume, then it is called as zero divergence. That here clearly what we need to remember is, the divergence is a term which will be useful for observing a particular field which is leaving the our volume, right? Whenever it is leaving, positive divergence. whenever it is entering the volume, negative divergence, the entering the volume and the same amount is leaving the volume, then it is called as zero divergence. So clearly remember, whenever we have some surface or closed surface that forms a volume, and if you want to calculate how much electric field is leaving through that one, or how much flux is leaving through that one, how much flux density is there, what we have to do is, if you want to calculate the leaving quantity, then we have to apply divergence over there. Then what we get is the leaving quantity. Now we will discuss about the cross product between the del operator and or unit vector is any vector called as curl. Let us take a bar is a vector. Then the cross product between this del operator and a bar is always called as curl a bar. Just already we know a cross product between two vectors. It's this del is a vector, a bar is a vector. So we can define this cross product in its determinant form. So if you consider the rectangular coordinate system, it was defined as the unit vectors in the coordinate system is ax, ay, az, and the components of first vector, since the del operator is defined as dou by dou x ax plus dou by dou y ay plus dou by dou z az. Now the components are just dou by dou x, dou by dou y, dou by dou z, the components of first vector, and the components of second vector ax, ay, az. This determinant gives us an answer which is in terms of ax, ay, az. So what you can understand is, whenever we are calculating the curl of any vector, what we get is a vector as answer. Now what that vector gives, and what is the interpretation of this curl? Now the name indicates curl always gives us curling nature. Curling nature means a rotating nature. Whenever the vector has a rotating feature for a differential surface what we are considering, then the curl will exist. Let us consider a field is there like this. Now what I am doing is I am placing a surface, a differential area like this. If this particular field can rotate that particular differential surface what I am considering, what you can say is this curl exists. If this curl does not exist, then we can say that this field is not capable of rotating. So a rotating nature of that particular vector or any vector a bar can be observed by applying curl on that particular vector. Now we will discuss what is different forms of this curl operator in the rectangular and cylindrical. Rectangular is already discussed, cylindrical and spherical coordinate systems later. So before that, just we observe what happens if del is equals to 0, what happens, or what is the interpretation of that one if curl is equals to 0. So del is equals to 0 corresponds to what, curl is equals to 0 corresponds to what, we discuss. After that one I will give you all the del operators for divergence as well as for curl in all coordinate systems. So here consider once again, let us consider a bar as a field. I am considering a differential volume here. For this differential volume I am going to calculate how much amount of the field is diverging or oozing out from the differential volume. So if the particular quantity is going out from the volume, then what you have to do is to observe how much quantity is going out, we need to apply divergence. Now if there is no field which is going out from the volume, then simply this divergence is equals to 0. That if the divergence is equals to 0, then what you can say is nothing is oozing out, as nothing is going out from the volume what we are considering. Then this condition is called as solenoidal, that the vector is called as solenoidal vector. The divergence is also always is equals to 0, right. In the same way, if you consider the field a bar, and if it is not capable of rotating, if it can rotate, it's how much amount of rotation, in which direction it is rotating, that you can observe using our cross product, that is called as curl, right. If you apply the curl to our a bar, you can observe the rotational nature of that particular vector. If it is not capable of rotating, then del cross a bar is equals to 0, that the curl always becomes 0. If del cross a bar is equals to 0, then it is called as irrotational. It is not rotational, the vector a bar is not rotational, then it is called as irrotational, or the field is conservative. So in the examination or in the problem, if there is any word like solenoidal, immediately we have to recollect that if it is solenoidal, the dot product of our vector with del, that is divergence, is equals to 0. And if it is conservative or irrotational, immediately we have to recollect that that has no rotational capability, that is the curl of this particular vector is always equals to 0. Now this same concept is applicable for all coordinate systems. So what I do is I will give you the forms of del in all the coordinate systems for this dot product, and that is divergence and curl. So in the rectangular coordinate system already we discussed what is our del dot a bar. So I will write del dot a bar in cylindrical coordinate system. Let us consider this a bar is taken in cylindrical coordinate system. So this del dot a bar is equals to, how this can be calculated? So same as our previous one. Here what we need to do is we need to take this del operator in cylindrical coordinate system, define a bar in cylindrical coordinate system, and just take the dot product between them. For our understanding, just what I am doing is I am writing the direct one, that is 1 by rho dou by dou rho of rho a rho component plus 1 by rho dou by dou phi a phi component plus dou by dou z a z component. So just this is the simple representation of our del operator with dot product, that is called as divergence in cylindrical coordinate system. If you are considering that one in spherical coordinate system, let us take this a bar is in spherical coordinate system, that del dot a bar is equals to, just it is written as 1 by r square dou by dou r square a r component plus 1 by r sin theta dou by dou theta of sin theta a theta plus 1 by r sin theta dou by dou phi of a phi. So if you want to apply our del operator in our spherical coordinate system for this divergence, this is the form what we need to consider. In the same way, the curl also I will give, that the curl, how the curl was defined in rectangular coordinate system, already we gone through that one, that is the determinant of ax, ay, az, the components of first vector, that is del dou by dou x, dou by dou y, dou by dou z, and the components of third vector ax, ay, az. Now here, how to define the same curl operator in cylindrical coordinate system? Let us consider the cylindrical coordinate system operation. Then del cross a bar, this is for cylindrical. Del cross a bar is equals to 1 by rho determinant of a rho, rho a phi, az, dou by dou rho, dou by dou phi, dou by dou z, a rho, rho a phi, az. So whenever we have cylindrical coordinate system as a function, then we have to use our cross product like this. In spherical coordinate system, the same operation, that is the curl operation between del and a bar, can be written as 1 by r square sin theta, the determinant of ar, r a theta, r sin theta a phi, dou by dou r, dou by dou theta, dou by dou phi. This is not capital AR, sorry for the inconvenience, they are the unit vectors small ar, a theta and a phi. Just we need to consider the unit vectors, not the components. Here we need to consider the components. They are ar, r a theta, r sin theta a phi. So what we have to do is we need to identify in which coordinate system the a bar is given to us, the function is given to us. Based on that one, we need to apply the del operator for our divergence or curl. So just we discussed about the three operations like the gradient on scalar, divergence on a vector and curl on vector. Now these three are discussed in different coordinate systems like rectangular, cylindrical and spherical coordinate systems. All they are just dou by dou r operations or dou by dou phi operations, that only the derivative will be taken with respect to phi r theta once. It's a single order functions. Now the same del operator can be applied on either scalar or vector with a double operation. It's called as a second order differential function. If it is called as a second order differential function, then it is called as Laplacian operator. So what is that Laplacian operator? I will define. The Laplacian operator is defined as just del square. This del square is called as Laplacian operator. This Laplacian operator is a peculiar function that this can be applied on both scalar and vector. So if you are applying on scalar, what it is called and how it can be interpreted. If it is applied on a vector, how this can be interpreted. Now we will observe the application of this del square on a scalar. Let us take V as a scalar. That del square V we want. So del square V can be written as del dot del. Always del dot del gives us the del square V. That is, the Laplacian of any scalar can be written as divergence of gradient of V. So if you are considering divergence of gradient of particular scalar, then it must be equals to the Laplacian operator. And if you consider a vector a bar, del square a bar. So del square a bar, if you go for the same analysis, then what we get is del dot a bar. Here this is an invalid one. That's why we can't apply the del operator directly on a bar. So clearly this analysis is not suitable for vector. So what we have to do is directly we need to consider this del square operator on A. So if you consider directly del square operator on A, the result will be like this. That is del square Ax plus del square Ay plus del square Az. So clearly remember that whenever we are taking a scalar, it's a Laplacian operator on scalar, this can be written as divergence of gradient of that scalar. And whenever we are applying on this vector, we are not supposed to write down like this. So instead of that, directly you have to write down this one as del square Ax plus del square Ay plus del square Az. Now we need to remember this del square is a very important operator for boundary value problems. In the electromagnetic theory, whenever we have a boundary value problem, to solve those problems, this operator is essential. So we need to remember how to apply this one and in which coordinate system, how it is defined. Just as an example, I will give this definition in rectangular coordinate system and we can refer the remaining two coordinate systems later. So in the rectangular coordinate system, it was defined as del square is equals to dou square by dou x square plus dou square by dou y square plus dou square by dou z square. So simply this is the simple function of our del square called as a Laplacian operator in rectangular coordinate system. Right? The remaining two coordinate systems we will discuss later or whenever they are required. So till now what we discussed is about the differential operator what we have. The differential operator is majorly one and only operator called as del operator. That this del operator can be applied on a scalar or vector. If it is applied on a scalar, what it is called? If it is operated on a vector, what it is called? Just I will give you a tabular form. The comparison of all those things I will write down as a table. Now just you analyze what are the topics we discussed till now related to the del operator. If this del operated on a scalar, then if this del operated on a vector, if it is operated on a scalar, it is called as gradient. That the name is gradient. If it is operated on a vector, that dot product gives divergence and cross product gives curl. Right? So what is the notation for this one? Gradient of a scalar V. Let us take V as a scalar and a vector is a bar. So it is gradient of V. Here the dot product, divergence of a bar, cross product, curl of a bar. Then if gradient of V gives, it's a maximum rate of change. Maximum rate of change direction. So in which direction? If this particular scalar quantity is varying rapidly, that can be observed using our gradient, and this gives quantity going out or oozing out, and this gives rotational nature. Right. If divergence is equals to 0, if it is equals to 0, called as solenoidal, and if it is equals to 0, called as irrotational or conservative. Right? Like that, just you need to remember, so what is our del operator and how it can be applied on a scalar, and what is the purpose of this one, how this can be applied on a vector in two different ways, and what is the purpose of this one. So if any function is given to us, and if the examiner asks to examine what it is, a solenoidal, irrotational, conservative, then what you have to do is you have to go for these operations. After going the operations, we need to examine the answer. If it is equals to 0, what happens? We need to just examine, right? It's apart from the single differentiation, we have one more thing, that is del square, called as Laplacian operator. So a Laplacian operator is a second order differential operator. All these are differential operations on a vector.